Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. This week, it is my pleasure to be joined by the wonderful Dr. Jackie Faherty, who is a senior scientist and senior education manager at the American Museum of Natural History, AMNH, and is also a recent recipient of the NSF Career Award, which is a 5-year research plan to study the local solar neighborhood in her case. So a very prestigious prize and a very well-known scientist. Jackie is most well known for her research on brown dwarfs, and she's even a co-founder of the local group here called the Brown Dwarf NYC group, or BDNYC, which sounds like a Korean pop band or something, but it's actually a real research group right here in New York. So brown dwarfs, what are they? They're something that you have maybe heard about in the news. They're kind of a strange object. They're not quite a star. They're not quite a planet. There's something in between, but I think that's what makes them so interesting. We don't quite understand how they form. We think some of them probably form like stars, but in a more diminutive sense. At the same time, there seem to be some which form more like planets, and has been very puzzling too. However, we are fairly certain that they are not stars in the sense that they don't shine, although they are still producing a little bit of light because of their faint infrared heat signature. They're still warm, so just like my body's producing some infrared heat, so too do these brown dwarfs. And so in that way, we've been able to study them using infrared telescopes like the James Webb Space Telescope over recent years. In fact, today, we're going to get into, well, first off, what is a brown dwarf? How do we define them? The different controversies that have been in the field over recent years. But especially, we'll be getting to new research on these objects. And JWST has been really a powerhouse for this. Remember, the James Webb Space Telescope is an infrared telescope, and these brown dwarfs, they shine in infrared light. So for the first time, we've really had the ability to study these things in enormous detail. So yet another feather to the cap of JWST. So we're going to get all into what these things are, the latest results, so please do stick with us. I hope you enjoyed today's episode. Jackie, the way I want to start is talking about brown dwarfs. This is an enigmatic object, but how do we define a brown dwarf? Do you have a personal definition, and how are the community defining brown dwarfs?
Yeah, why don't I start by telling you the definition I hate?
Let's do that.
Because that's a good way to always start. And then I don't want to have to use this definition again. But it's in the ether, so we might as well say it out loud. And that is that brown dwarfs are often defined as failed stars, meaning that they probably try to form the same way stars form. There's a giant molecular cloud, it collapses, it fragments into pieces, lots of pieces break off, big ones that make big stars, small things that make small stars. But then there's this limit where something breaks off, where its mass isn't enough to get the core hot enough for nuclear burning to occur. So in that sense, the object that breaks off, that fragments off, fails at becoming a star. Now, it just means that it's the smallest fragment of star formation. The word failure is never good to use in the title, which is why now we can just acknowledge that some people have said it, and then we don't have to use it again. Because there's more positive ways to describe what a brown dwarf is. They're objects that sometimes I'll call overexcited planets. Because
overachieving planets.
Overachieving is also another way to say it. They are in between stars and planets. They exist. Maybe they form like stars, although we don't know if they could also form the same way giant planets do. So formation is a hard way to define them. But in mass, they are defined as objects that cannot get nuclear burning going. And that happens around 75 times the mass of Jupiter. Mm-hmm. Then at the low mass end, sometimes people will use another mass arena for their definition. And that is that at 13 times the mass of Jupiter, you do not get heavy hydrogen burning anymore. So below 75, you can get heavy hydrogen to burn. You can't get stable hydrogen to burn, but you get deuterium burning. Mm-hmm. And then below 13 Jupiter masses, you just can't at all. And so we kind of call things below 13 planets, things above 75 Jupiter masses stars. And then the in-between are the amazing brown dwarfs.
So a failed star, we normally, when people hear about failed stars, sometimes it's with Jupiter, don't they? People say Jupiter could have been a failed star, but that's
Yeah.
way off
Yes, way
the limit
off.
you're talking about. Although these objects probably have a similar size, but a very
Yeah.
different mass.
Right. So it is. Sometimes people will call Jupiter a failed star because it's the biggest planet in our solar system. You could fit the mass of everything besides the sun: Jupiter, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, the whole Kuiper belt, the whole asteroid belt, everything inside of Jupiter. It's so massive that it felt right to say to somebody, not me and not you, somebody, it felt right to call it a failed star. But it's nothing like that. It's a single Jupiter mass is nowhere near the boundary by which we would consider it forming the way that stars form, at least not in its current position around the sun. So Jupiter's definition of a failed star is just kind of a red herring.
Okay. It feels like an awkward category in a sense then, because it's kind of shoehorned between stars, which we've known about since antiquity, planets, which, of course we know also since antiquity, but then exoplanets came along.
Yeah.
And then we started to find these brown dwarfs, and feels like we didn't know what to do with them. When was this era of discovery? When was this all kind of happening, that the brown dwarfs were being discovered?
Yeah, so it's in the late 1950s, early 1960s, where the theory emerges, which says the end of star formation processes will yield this kind of object, which will be small in mass, 75 Jupiter masses or below, and at that mass, it's not going to be able to have stable burning. And at that point, people were still trying to find the lowest mass stars that are tenths of the mass of our own sun. And that's where the state of things were for stellar searches. You had to wait until infrared technology came about in order for brown dwarfs to actually be discovered. So in the 70s, the 80s, and then the early 90s, searches were on for brown dwarfs. People were hunting to find the very first example of this exotic object that was predicted. So it was probably 3 decades of searches.
And how were they searching?
It was optical surveys at first. The prediction was that these objects would be very cold. They'd have to be if they lack nuclear burning, so they'd be very cold. Mm-hmm. And so the searches were looking for the reddest possible objects that one could find. And actually, the best way to find them would be if you also had the motion of the object, because you'd want something that was very red and moving rather fast, indicating that it was close by. And that would be your trigger. So the early studies tried optical, but optical wasn't the greatest because these objects are actually quite faint for the optical. So it was a lot of fishing with no yield.
That's interesting, because I think, is it true that with JWST there have been these very red objects? When I think of very red objects, my mind immediately goes to these galaxies that, of course, there's been so much interest in. Your head's in the brown dwarf space, but there are people thinking about the reddest objects being these very high redshift galaxies and the earliest things forming in the universe. And so I think it's true that there have been some cases where these sources, which were maybe thought to have been very high redshift things, were in fact candidates for being brown dwarfs close by. So then you have this degeneracy. There's just a red source, and it's that motion. But if it was a very distant brown dwarf, you're kind of stuck. You'd have no way to delineate those.
Yes.
Or if it was just happened to be very still.
Right. So there's 2 things. One is that in the earliest brown dwarf studies, there were 2 major missions that did a lot of the bulk work of finding brown dwarfs in big numbers. One was the 2-micron all-sky survey. That was an infrared all-sky survey, and that's why it really cracked open brown dwarf studies, because it moved us out of the optical, where brown dwarfs are very faint, and into the infrared, where they're giving off the majority of their light, and all of a sudden they were found in the hundreds. Then there was also the Sloan Digital Sky Survey, which was also, it's not all sky, but it goes pretty deep in red wavelength light. And the early Sloan surveys did make a big dent. And some of the earliest big papers on brown dwarfs were written by extragalactic people, by people that study quasars and active galactic nuclei, because They're also looking for the reddest sources, similar to what you're bringing up about what we're now finding with JWST, because the earliest brown dwarf searches, they didn't actually have proper motion yet. So they couldn't use the motion like I just described. That came a little bit later. But the early studies, they did use just the colors. They were looking for colored objects that are very red in maybe 2 different colors. And there's an overlap between quasars and brown dwarfs, so that quasars are my garbage. So I find quasars every now and again. I find these galaxies that I do not want, and I hand them over to them. And then they find these brown dwarfs that they do not want, and they hand them to me. And both of us get so happy by the other's junk. So
one person's trash is another person's treasure. Right?
Very much trash and treasure come together here with extragalactic and galactic.
That's nice to. And how many brown dwarfs do we have now? I mean, what's the catalogue look like? Is it all confirmed candidates? What are we looking at?
Well, so brown dwarfs are really limited in volume to how far out we can see. But our spectroscopic catalog, meaning the ones that we identify, you found that they were very red, they were moving, and then we followed them up with a spectrograph, and we got a spectrum that showed us how cold the object was. That's in the thousands, several thousand of those. There's also this issue.
So they're slam dunk? They're like, we definitely sure those are brown dwarfs?
Yeah. Nailed it. Like super slam dunk. But here's a little bit of an issue. The early studies of brown dwarfs, the ones that people could find easily were the warmest ones. The ones that are, they're temperature-wise, our sun comes in at like 5,000 degrees Kelvin. These objects come in at, say, 2,000 degrees Kelvin. So they are maybe 2,500 degrees Kelvin, I should say. I'll go to the warmest ones that were found first. But brown dwarfs have this issue. They have a degeneracy. If you don't actually know the age of it, because it doesn't have stable nuclear burning, you're not totally sure how massive it is. So you can't really know if it is above or below that 75 Jupiter mass boundary I was telling you about. So the earliest type, the warmest objects that we call brown dwarfs, might actually be low mass stars. So the spectral classification that we use is there's late type M's. That's the end of the stellar sequence that everybody's kind of comfortable with.
It's like TRAPPIST-1 or Proxima Centauri, these kind of famous exoplanet systems would be examples of those.
Yeah, so Proxima Centauri is a definitive star. It's an mid-type M. But then TRAPPIST, I had studied TRAPPIST as a brown dwarf scientist because we weren't quite sure if that one, where it's at the teeter-totter boundary between a late type M, it's a late type M, and then you get into the L's, and it's the L's that people are like, okay, we're in brown dwarf territory. But really, it's not until the mid-L, until you're like halfway down the L sequence, where I could say, even if it's as old as the galaxy, your mass is going to definitely be a brown dwarf. So this is the elusiveness of brown dwarfs. Without the age of a brown dwarf, you actually aren't sure, unless you find a super cold one. And the super cold ones, which we call the Y-type brown dwarfs, there are only about 45 of those known or so. And there, maybe only 25 of those have a spectrum, so they're definitively confirmed.
Is there any risk of those being free-floating planets rather than brown dwarfs?
Oh gosh, you just asked a very controversial question. How would you define a free-floating planet? Well, how would you define a free-floating planet?
Well, I have some. We'll get into that maybe a little bit. It's not really I don't really have a strong opinion on this, but there's a couple of papers I thought we could get your reaction to definitions on this.
Okay.
But I guess we have this category of these things which are so hot they could be a star, and then we have these very cold brown dwarfs, which possibly could in fact just be a Saturn.
No, that would be nutso.
Okay.
That would be so cold.
Okay.
So that's very low mass. Some of them,
because they just cool too fast.
Yeah, they can't be Saturn. But if you want to say, like, could they be 3 Jupiter masses or 5 Jupiter masses? That's the gray area.
Right.
I've got a lot of 3 to 5 Jupiter mass objects. The youngest warmish ones are also that mass range, 3 to 5 Jupiter masses. Because I study brown dwarfs at all ages. The ones that I get most excited about fall in two categories. One are just extremely cold, so they'll be super low mass just because their temperature's so low. The only way you can have that low of a temperature is if you're low mass. Even if you started off hotter, it's not a lot of time for you to get to like 3 to 5 Jupiter masses.
Even in the age of the universe.
Yeah,
it just has to be low mass.
And then there's the really young ones. So I go after those as much as I can because you can find them hot and isolated and they're very low mass. So I can find 3 to 5 Jupiter mass ones that are hot still.
So these are in clusters, like in star-forming areas, essentially?
Yeah, well, star-forming areas, there aren't in star-forming areas like Orion or Upper Sco or ones that you might think about, or Carina. They're in things like the Beta Pictoris moving group, the Tucana-Horologium moving group, which our sun is actually surrounded by a bunch of these loosely bound young stars that are just sort of washing over us. So I go after those because the brown dwarfs, we need them to be close by. All the major star-forming regions are a little bit too distant for me to be super happy with to get spectra and really study things. I need the ones that are on top of us.
So we have this. This is a minor point, but for the spectral classification, I was always taught. I know it's probably not PC now. Oh, be a fine girl and kiss me, right?
Yeah.
Or girl or guy, you can replace that. But that's the spectral classifications going from the high mass to the low mass. And M there, kiss me. M is the last one of that. And so to go into the brown dwarfs, you have L after that, and then. What comes after that? Is there a T?
T.
And Y?
And then Y.
So
you got it.
Yeah. How do you
What's the mnemonic?
Yeah. How do you remember that?
There are mnemonics for this, and Astro 101 classes will try this, but I don't think I have a good one that extends off of Oh, be a fine guy or girl. Kiss me later that day. I think later that day is what some people will say.
Like emphasis on the Y. Okay.
Yeah. It's a hard one because you got to get a Y in there.
Well, that's a homework assignment for our listeners to come up with their own fun correct one. So, this is a curious topic. When I was studying, and learning about astronomy, there was only a few exoplanets that had been found, and it's kind of show my age a little bit, but it was still kind of a new field. And I remember I only did like one lecture at Cambridge. This was about exoplanets. I think it was just seen as like this little, you should do cosmology, but by the way, there's this exoplanet thing on the side. And that's how I kind of ended up doing exoplanets. I don't think I'd even heard of brown dwarfs at that time. How is it that you discovered them personally and ended up championing this as a cause? Because now you have this, we should say you've got this enormous group here, BDNYC, that, is doing all this amazing science in New York City on brown dwarfs, and you really are one of the main champions of brown dwarfs in the whole field right now. But what is the journey personally for you to find this field? Yeah,
well, when I started, I also don't want to have to age myself too much, but brown dwarfs were still rather new. So I started on my thesis project, like trying to decide what I was going to do back in 2006. The first brown dwarf was observationally confirmed. There's a little bit of a debate on this.
Okay.
Because there's two different brown dwarfs. One was a very hot one, and it was a late type M, and it was young, and so people want to call that one the first one. But that's in the grayer area. The one that many people note is called Gliese 229b. It was a T-type, so it had methane in its atmosphere. It was definitely cold. That happened in 1995. So when I started in 2006 trying to decide, it had only been 11 years. And at that point, what I liked was that I was hanging out with a lot of people socially that worked in the brown dwarf field. I had actually taken some time before graduate school to work at the American Museum of Natural History in the education department. And the co-discoverer of Gliese 229b was there at the time. Her name is Rebecca Oppenheimer. And Rebecca was such a champion of brown dwarfs because she had been the co-discoverer. She'd been at the telescope when Gliese 229b was discovered. She was there. She was the one that observed it.
Yeah.
And then her very good friend was somebody named Adam Bergasser, who defined the T-type classification after Rebecca discovered Gliesa 229. And I thought they were really nice people. They seemed fun.
Yeah.
And because of that, I was like, oh, a young field where there are fun people. And as you know, when we pick our fields, we're kind of picking the people we're going to be around a lot because
For years.
forever, maybe,
Yeah.
unless you switch your subfield. And because of that, I was actually somebody very aware that I wanted to be around good people. Plus, brown dwarfs were young, and that felt like there was room for me. I didn't want to enter a field that was uber competitive and that everybody was going after the same big question. There were all these open questions for brown dwarfs, and I could do the very basic kind of work that I really like to do. Like, they still needed motions measured. They needed a workhorse, and I was very willing to be the workhorse. So that's how I began, with nice people and tasks that I thought were fundamental and easy to get my head around, and that just it's worked well. And
I think we have a similar situation then. I mean, when I was thinking about exomoons, it seems like people ask, why did you get into exomoons? It's just a strange thing to do. But it wasn't so much people I wanted to work with, but people I didn't want to work with that drove that decision. I remember I was supposed to be doing atmospheres as my first topic. I don't want to, put down atmospheres the whole community, but I went to one of my first meetings and there was atmosphere people just screaming at each other at this meeting. They were like so angry that one person disagreed with each other. And I was like, whoa, this doesn't feel like an environment where I want to like stick my neck out. And especially as a first year of PhD. So I ended up sort of finding exomoons as like this little, back of the room topic where it was much quieter and it felt like you had some space and people weren't going to be just slamming down on you for every little thing you said. And that to me was also a big part. I think both of us are interested in this subject area that we've chosen, of course, but I think people underestimate how important it is, the actual climate of the field to choose. That's good career advice, I guess. You'd say for other people.
Yeah, I don't know that people realize how much of doing science is working with people. So I often get asked about being a woman in science or being, well, I used to be a young woman in science. Like, how does the age end up working for you? Still, right? Thank you. Thank you, David. But all of these things that are not, if all we were doing was sitting there on a computer or with a pen and paper, then none of that would matter. The people that you're around, being a woman, being a man, wouldn't matter. You would be just some agnostic number or something. But that's not what's happening. We are actually talking to each other a lot. We are working with each other on projects, especially like I chose to be an observer, not a theorist. So theorists can isolate a little bit more. But I chose the work of somebody that goes to telescopes and that you have to be in collaborations when you're an observer. It would be very difficult to be a lone observer. So all of that does require you to pick people to work with. And I'm very careful about that in my own work. I'm careful with my research group that I'm training people to be good people later as well, so that the brown dwarf field continues to be one like what I saw when I entered. Good people, fun people, collaborative people, people that anybody would want to work with. This whole atmosphere thing, you're right. People screaming at each other in a conference room. I don't want that. How is that fun? How is that fun to go to meetings and just be stuck in a screaming match between people? I definitely don't want that. And I don't want that for my field. So I definitely am one of the advocates for keeping at bay any bad apples that might be around so that our community remains peaceful and happy. And that's what I think the leaders in our field should really be doing too.
Yeah, I like that advice a lot.
Yeah.
And, brown dwarfs, I guess as it's becoming more prominent, there are more controversies and discussions happening about, especially the definition thing, which I'm sure, it's interesting to explore a bit further. There's this deuterium limit that we mentioned before, and you said it's around 13 Jupiter masses. So this is the point, just to be clear. So hydrogen burning inside a star, like a single proton fusing, that's what makes stars shine when we think of a star like the sun. These brown dwarfs, they also have some lower level of fusion happening, but it's deuterium, which is a heavier isotope. So that's a proton and a neutron stuck together, and those confuse. But I guess it's just there's hardly any deuterium, right? I think there's only like 1 in every 100,000 hydrogens is a deuterium, so there's not much of it around. Doesn't produce as much energy as I think a hydrogen 1 fusion reaction does. So these things have a bit of internal energy, but it's not enough to shine. And yet there is still a lot of controversy about where this point happened. So there's this paper, one of my friends who left the field, Dave Spiegel, wrote this paper. You probably know it.
I love Dave.
Yeah, he was actually here at Columbia as an undergrad.
I know, yes.
Yeah, so that's maybe where I don't know if you knew him when he was in the city.
I did. Dave was a grad student too here.
Oh, maybe he was a grad student?
He was a grad student.
Maybe
I
both.
don't think he was and then he went on to work with Adam Burrows at Princeton.
Okay. Well, this is the paper with Spiegel, Burrows, and Milsom, and they found that 13 Jupiter mass limit corresponds to when 50% of the initial deuterium can burn. But if you change the metallicity or you change that fraction, you go from 50% to 10% or 90%. It's who can decide where that special percentage is. Then it goes from anywhere from 11 to 16 Jupiter masses, and of course even then you could probably push even further and argue about it. So does this actually have any utility, this deuterium thing? It seems like it's such a wide and disparate region. I'm kind of questioning whether this really is useful as a definition for a brown dwarf.
I don't think it's useful at all. I think that astronomers have, on top of the fact that I don't think it's useful as a definition, there's no way to measure the deuterium either. We can't actually, there's nothing I can observe for you and say, okay, I've got a deuterium burner here, or okay, it had deuterium burning X number of years ago and it's done. Because the deuterium burning doesn't last very long. It lasts in the early stages of
I didn't know that.
Yeah, so it only lasts for a little bit of time, and it keeps it like nice and bright for a bit when it's young. And stars have it, like low mass stars do it too, but it's I can't measure anything to tell you it's a deuterium burner. There's no deuterium line I can go and get for you. So that's the other reason or that's a primary reason why I don't think it's very useful. But because, as you just mentioned, there's a lot of like these caveats about what the deuterium burning limit really is. I told you 13, but I should have given you the caveats around it, because it can be metallicity dependent. It can be dependent on a lot of aspects of the object itself. So what it is, though, is that astronomers have a very annoying desire to put things in
buckets.
Yeah. And this is a bucket that people thought would work. And it is a bucket that I have said in papers reluctantly, just because it's out there, but it isn't one that lets me answer a next level important scientific question. It's just like the word planet. Planet is a bad word too. How does that help me calling Pluto a planet versus Pluto a dwarf planet if I want to study some atmospheric property of Pluto versus an atmospheric property of a moon of Saturn? Why do saying the word planet mean something scientifically? Because they end up not meaning anything. 13 Jupiter masses for deuterium burning or not is also not telling me much about the object. Maybe it had deuterium burning, maybe it didn't, but does it tell me something intrinsic about how the object evolved? Because I can't measure the deuterium burning, no, I can't use this at all.
Okay.
So I hate it.
So I totally hear what you're saying about this classification being kind of silly, and certainly with planets in the solar system, that's, I've said that many times on my channel, that like, why does it matter? Like, a rose beneath the name still smells as sweet. Like, what we call it, Pluto doesn't care what we call it, right? And in the same sense, these brown dwarfs don't care what we call them. But on the other hand, it seems like Jupiter is very different from these canonical fiducial brown dwarfs, however you want to define them, which, presumably Jupiter did form in a very different environment, in a very different pathway to these objects. And so it is reasonable to want to put them into different populations when you're doing your demographic studies, right? Because otherwise you're getting contamination between these two different pathways. Yeah. So there was another suggestion, you're probably aware of this one as well, by Kevin Schlaufman. Mm-hmm. And he said, just, forget about the deuterium stuff. Great, happy with that. And just focus on how it formed. That's all that matters. Did it form like a star via gravitational instability? So that's just a big cloud of stuff fragmenting and collapsing under gravity to to form stars or these brown dwarfs, or did it form like a planet? We define planet, and I guess here his definition of planet is it forms by basically core accretion. So you start with small pebbles and they accumulate, they coagulate, and they build up and up and up until you form a planet. And he, in this paper in 2018, he argues that there is a break at around 10 Jupiter masses that seems to split the population between things which look like they form like stars, things which look like they form like planets. There's probably some contamination either way. It's not like a clean break, but if we wanted a rule of thumb, that might make more sense. I'm just curious about what your reaction to that suggestion would be.
Yeah, that paper by Kevin was a nice paper. It's something we've all said. And Kevin was really focused on the higher mass planets in that paper. And not to dissect Kevin's paper, but there are positive things in it, but then there's also some flaws in looking at the population, the way he broke it down. If there was some smoking gun to formation, I'm the first to jump on board. There's a small hint in Kevin's paper at the possibility of a formation break, but there is nothing yet that we have uncovered that can be used on a large scale portion of the population to observe them, look at all of their properties, and say, okay, we've nailed it. This formed through core accretion. This formed through gravitational instability. This formed through molecular cloud fragmentation. There aren't observational signatures yet. That is something I'm working towards. Myself and my team are working towards observational signatures in detailed spectra of objects that are companions, close-in companions, wide companions, isolated objects, objects that have other companions inside and outside of their orbit. There's many different things that might tell the story of the formation of the sources. And you need to look at so many objects before you could really nail down the smoking gun of I know how it formed. But if we could, I am very on board with using that observational signature as saying this thing is a core accretion object, this thing is a gravitational instability object, this thing is a molecular fragmentation object. Maybe we'd even find some new formation mechanism signatures. But
if it's isolated, though, doesn't that? I mean, that seems like it narrows the options, right? How do you get core accretion in just interstellar space? It seems not really plausible. That surely must be
you'd eject it. It would just be an ejected object.
Yes. Okay.
Yeah, not core accretion on your own.
Yeah.
You're going to form through, when we find the objects on their own, you were alluding to before, if you found like a 3 Jupiter mass object, could you be a free floating planet? A free floating planet is also a term that gets used for both things. Are you free floating because you formed at that tiny little mass and off you went? Or are you free floating because you got kicked out of your system? It is totally possible to eject. We've probably ejected planets from our solar system when we formed, and we even see things like the HR 8799 directly imaged planetary system for very large Jupiter mass worlds, very much akin to brown dwarf sizes. They were just a bit farther away from their host star. No one would say boo about calling them brown dwarfs, but they're closer into their host star, and so we call them planets. But they're not super stable. They're probably going to get loosened up, and they're gonna lose. Some of them are going to lose out.
Are those brown dwarfs to you? Like, where do you personally draw this line?
I don't draw the line on systems like this. I include them in all of my objects. To me, are observed things. I look at their spectra, I look at their photometry, and I try and decipher things that are happening in their atmospheres or in their evolutionary state. Do I care if I have this debate with my team all the time because, like we say, in astronomy, we like buckets. And I have to send my research proposals and press releases and whatnot down a bucket. Am I studying the brown dwarf or am I studying the planet? And unfortunately, sometimes we have to make this decision strategically. So if I was going to attack to a time allocation committee, I don't want to go to the exoplanet panel, because you've noted the exoplanet community can sometimes be a bit cruel. So I choose a different tack to say my research is under. But they're really planets too, at the level of the excitement they should bring. And so sometimes I'll choose the word planet because people need to feel it. And we don't have a good word for the exciting brown dwarfs. How do I get you excited about a brown dwarf? I'll tell you it's a planet.
Yeah.
And then you're going to be like, wait, what'd you say?
Yeah.
Did you say planet?
Well, I like you. I think you've said before, worlds is probably a good
I like
catch-all.
worlds.
Just,
yeah.
I've used this a lot for Pluto and for the moons. Like that's just not argue about what they are. Just use worlds.
Just use
We
worlds.
actually wrote, you probably know this paper we wrote with Jingjing Chan years ago called Forecaster.
I love that paper.
And we called everything worlds very deliberately.
Really well done.
Because we didn't want to get into all of that. So one of the most fascinating things I think about brown dwarfs, when I first was learning about them, like the lumen objects that were being discovered and stuff like this, is when I was first encountering these. And they are very faint, and as you've said, they can have temperatures which are extremely cool, even room temperature.
Yeah.
Right? There is some room temperature brown dwarfs,
Yeah.
which is, the surface is room temperature.
Yeah.
Obviously, deep down, it's probably much warmer. But that's amazing. First of all, you can think about just standing on the surface of that brown dwarf, and yes, the gravity would be crushing, but you would not boil off on the surface. It's kind of fun. But it's also intriguing because there could be therefore brown dwarfs which are even cooler than that, which are sub-room temperature, and therefore they could be really close by, maybe even closer than Proxima Centauri, which is the canonical closest star to the solar system, 4.2 light years away. So there could be a brown dwarf closer than 4.2 light years away that we've just haven't discovered yet. I always thought that was such an intriguing idea, especially for those of us who dream of setting out an interstellar spaceship one day, that the brown dwarf could be the destination. Is that idea still alive, or have observations now kind of quelled that? Has it been ruled out at this point?
Well, you're setting me up for I have a citizen science project that I work on that was founded on this exact thing. So most people can name the closest star. Usually they say Alpha Centauri, and it's Proxima Centauri, but...
Kind of right, because it's a triple star system.
Right.
Yeah.
Close enough. Not a lot of people can name the second closest star, which is Barnard's star. Almost no one can name the third closest system to the sun. That one is a brown dwarf system. It's called...
Is that Lumen 16AB?
Yeah, Lumen 16AB or WISE 1049AB.
Okay.
So it's named after... Kevin Lumen was the discoverer of it, but it also has more of a coordinates name, WISE 1049AB. And then the fourth closest system to the sun is another brown dwarf. It's called WISE 0855. Now, those two objects, the third closest and the fourth closest systems to the sun, were only discovered a decade ago. 1 decade ago. This was always bigger when I've been giving this speech about them on a regular basis. And so in 2010, 2011, or 2012, 2013, when they had just discovered, and I could say to people, did you know we just discovered this yesterday? Felt like so crazy.
Yeah.
Now, when I saw Kevin Lumen's paper, discovering WISE 0855, the coldest compact source that we know of. When you talk about these cold objects, they have to be close to us to detect it. WISE 0855 is just 100 degrees Kelvin warmer than Jupiter. That's it. Just 100 knots above on the thermometer. I saw that and I was like, all right, there's definitely one closer than Proxima Centauri. Why is the fourth why is it so close to us? It's actually supposed to become less efficient to make these kinds of objects as you get down to those low masses. Because at some point the star formation process becomes inefficient. So at least we had no idea how many to expect at the low mass end. So my mind was blown when this was discovered. And there's so many things about this. So I was like, oh, how did he do it? How did he do it? You want to know how Kevin did this? He blinked images. Night after night, just him. Thousands of images every night. The same way Pluto was found, by blinking images to try and find something that moves. This object, because it's so close by, it moves. And he used NASA's Wide Field Infrared Survey Explorer mission data, which is in the mid-infrared where these things are bright. And he saw it
by
jump.
Eye? Just looking at a screen. Yeah, wow.
All he did was download thousands and thousands of images and blink them. First, he found Lumen 16AB, third closest system. And that thing is actually bright. And we should have found that one as the first brown dwarf system. But it's towards the galactic plane where it's crowded. And so people had just missed it. WISO 855, you could have only found with this mid-infrared data. But Kevin found it. The WISE team had gotten confused about it because the original image was sitting on a galaxy and it confused the photometry. So they actually kind of missed it. I was on the WISE team. Or I was an ancillary part of the WISE team. So I knew we had missed it. When Kevin's paper came out, I was like, oh my goodness, what is this? So after that, I was like, that's it. I'm going to blink images. I'm doing it. I'm doing it too. Kevin did it. I'm doing it. I bet there's something closer. But then a guy named Mark Kushner came to me and said, why don't we use a citizen science project to do this? Why are you going to blink these images, Jackie? And I was like, excellent point.
Because he's the Disk Detective Program as well, right?
Yeah.
Which, I think he's been on the channel years ago and spoke about the Disk Detective Program for citizen science. But so this is a separate, this is all on zooniverse.org?
Yes, it's a Zooniverse. All of these are Zooniverse citizen science projects. Mark is now the ambassador for NASA on citizen science. He's awesome. And he had been working on Disk Detective, and he actually gave a talk at the place that I was a postdoc at the Carnegie Institution for Science in the Department of Terrestrial Magnetism on Disk Detective. And he had all these throwaway red objects that looked like they moved. And I was like, oh, I'll take them. He's like, does anybody want them? And I was like, I do. And he asked me why. And I said, because I'm looking for something
one person's trash again.
Yeah, I was like, I'm going to take your trash. I'm going to look through it. I'm going to see if there's a cold object in there. And then I told him of this quest I had that 0855 had shown me. Maybe there's a brown dwarf closer than Proxima Centauri, and thus launched this project called Backyard Worlds.
Hold on. If it was a Jupiter, let's say it was just Jupiter, had the same temperature as Jupiter, same radius and mass as Jupiter, but we're going to call it a brown dwarf, how close would that have to be detectable?
Yeah, so for those, Kevin did a pretty good analysis and basically outruled that Jupiter or Saturn might be detectable in our surveys to date. So the Wide Field Infrared Survey Explorer and 2MASS, both of them had as like little submissions to find the coldest low mass object around us. Maybe the sun kicked out a almost brown dwarfy friend. And there's something called the nemesis hypothesis, that our sun actually has a companion. And it can't be a star at this point. We would have found it, or at least that seems to have been outruled. Could it be a brown dwarf companion? Could it be a really low mass brown dwarf companion? And so Kevin Lumen wrote a paper that really analyzed the Wide Field Infrared Survey Explorer data. And I can't remember how far out he ended up going to say to eliminate Jupiter or Saturn as part of like another one of our solar system objects, or even a low mass brown dwarf out to a certain distance that would have been our friend, our nemesis.
But that sounds pretty bad news. And what hope is there then with your project? What are you looking for?
You could put a younger one. You could put a younger one farther out, and a young one is hotter. So
further out than Proxima, or how would?
No, within Proxima.
Okay.
So take a brown dwarf and make it younger. Like this has been this curiosity about WISO 855, maybe it's younger. It's this thing that I've mentioned about if it is, you don't know how to differentiate the age and the mass of the object. If you don't know the age, you don't know the mass. So you could have, Jupiter was way hotter when it was young. So it was way brighter. So you take an object that's, let's say 3 Jupiter masses and stick it between us and Proxima Centauri. Can you still hide it? You could still hide an object like that between us and Proxima Centauri.
So to make it detectable, you have to make it hot?
Yeah, to make it detectable, it needs to be warmer.
And therefore young.
So younger. Not more massive, just warmer. So a low mass object that is just on the young side. And we're surrounded by young objects. Actually, my colleague Jonathan Gagné and I worked on a project. We were constantly looking for young associations near the sun. And Lumen 16A and B, or WISE 1049AB, the third closest system to the sun, it was really interesting. It's really interesting on so many levels, but we found a new association that it's a part of. We called it Oceanus.
Nice.
And it's co-moving with it. So it's part of a family of stars that's just washing over us, and it's just a couple 100 million years old.
So we can detect a 3 Jupiter mass object that's closer, that could be the closest stellar object. I don't know what to call it, but stellar world.
Brown dwarf. Just a world. Just a world. Let's just call it a world.
There could be this out there, but that doesn't preclude then there could be an object which is not young but old, would be even colder, even fainter. But we just have, I guess what you're saying is there's just no way of looking for that.
It's just hidden.
Yeah.
I mean,
that's like Planet 9 type territory that it gets almost undetectable.
So some of this, it's the limits of the surveys that we currently have. So Mark and I started Backyard Worlds, and what we were doing in Backyard Worlds is very, very detailed searches of the Wide Field Infrared Survey Explorer, not just with Kevin type eyes blinking back and forth, but we enlisted about 50,000 volunteers, and we've gotten a number of them that are just amazing, and we call them super users. And we more than doubled the population of coldest brown dwarfs known. We didn't find any that were closer than Proxima Centauri. Otherwise, we'd
know about it. Yeah, there'd be a news splash, I think.
Right. But we did find a lot of them that had been previously unknown that are within spitting distance away from us, that have been redefining our local solar neighborhood. Lots of them. We found lots of them. We haven't found one yet. I'm not giving up hope. And Kevin's limits, when I was saying like there's not a Jupiter or Saturn attached to our solar system that's like just a little bit further away. But that doesn't mean that there's some windows that I think we could still play with, where there could still be an object that's cold, that's out there, that we just haven't found yet. And that maybe JWST deep sky imaging is just not all sky. We're going to be able to blink some images and find something that just hauls across the sky and is in the mid-infrared. We could get lucky.
Yeah.
I'm not going to give up hope.
Yeah, it's exciting. It actually sounds like the perfect sort of thing for like breakthrough to go after, because they want to find this interstellar target, right? Or they would love it if there was a closer interstellar target.
Yeah.
I don't know. It could be an interesting conversation, those guys, to get them excited about that. I want to talk to you about companions to brown dwarfs.
Okay.
Of course, because that's something
Moons.
we're interested in. Yeah. So there's one of the first directly imaged exoplanet is, I think people would argue about it, but it's 2M1207, and it's a 25 Jupiter mass brown dwarf.
30,
at least,
yeah.
Okay, we can argue about the mass, but somewhere in that ballpark, with a companion around it, about 50 AU away, that's around 5 to 6 Jupiter masses. And so, there's other examples like this as well. So we know that brown dwarfs sometimes have companions, massive companions. That's fairly assured. And then we have TRAPPIST-1, which is almost a brown dwarf, right? It's almost flirting with its mass of being on the edge of what we would call a brown dwarf, that has this rich system of 7 small rocky planets around it. So we have brown dwarfs with massive Jupiters around them, and we have almost brown dwarfs with lots and lots of what looks like the Galilean moon system, really, just kind of like scaled up a bit. Yep. And you get TRAPPIST-1. And so it seems like these brown dwarfs must have companions, at least, especially rocky companions as well, given all these hints. Have there been any searches? The one I was supporting but never happened was Amori Triad. Mm-hmm. Had a suggestion to use Spitzer. It was like a gigantic number of hours, like thousands of hours of telescope time.
It was the entirety of what Spitzer had to offer.
Okay.
He asked for all of it. I was also supporting it.
It would have been wonderful though, because that would have been a real Kepler-like survey almost of brown dwarfs to look for these companions. What do we know of possible companions to brown dwarfs right now?
Yeah. Oh, so many things.
Especially small companions.
Right. Well, I can plug one project that's called PINES. It's the Perkins Infrared, I don't remember the Nearby Earth Survey. So what PINES, which was led by Phil Muirhead at Boston University, did.
I know the project, yeah.
Okay, so PINES, which was awarded a NASA XRP award, which was the Exoplanet Research Program award. I was a collaborator on it along with other members of my team. where we've selected a number of the closest brown dwarfs, the L's and the T's, in order to go after them for transiting rocky worlds. There is one published candidate that looked interesting. It's a dicey one. We in no way we're saying we found it, but it was an intriguing candidate. The reason why this is hard to do, say you want to do the transiting method, which is where you stare at the object and you watch the light dim, to find a rocky world that transits, is that brown dwarfs are variable for a different reason. They have clouds, complex cloud patterns that you have to get past, and they're erratic and they're not as easy to get rid of as, say, a star spot might be. So getting rid of brown dwarf clouds is a or understanding brown dwarf atmospheres.
So variability. They're very variable.
Very variable. Yeah. So that's hard. So you could look at, there is one result that we have which people could look at, though it was too tentative to say much about. Then there was Stan Metchev ran a program as well where he used Spitzer, not the Amori style, Amori triad, who did try and say, I'm going to give you the biggest possible idea I can have. Let's take all of Spitzer Space Telescope's leftover time and use it to survey brown dwarfs for a rocky world that might be around that. That clearly didn't go through because it was asking for every lick of time, and that never goes through. But Stan had a great program to stare at objects, to stare at brown dwarfs with Spitzer. And one of the ways that you could do this too is figure out, you need to look at it equator on. You don't want to be looking at it pole on to try and find your rocky worlds.
Okay, makes sense, yeah.
Yeah, because if you look at it...
to form in the disk around.
Yeah, right. So we orbit kind of the disk, the plane of our solar system. All of us are kind of hanging out around the disk of the sun. And that's the
and
typical...
Jupiter's moons do as well.
Right, and Jupiter's moons do, right. So that seems like a logical thing. If you're going to start eliminating stuff, don't just blindly survey objects. Survey the ones that you know are equator on. Stan had a nice, he found a bunch of objects in Spitzer, and then he tried with the Transiting Exoplanet Survey, TESS. So there have been all of these attempts. They have not yielded anything yet. This is
any upper limits? Do we have any?
We may have published some numbers in a Pines paper as to what, in the proposal, we had a prediction based on TRAPPIST, as you note. It's an M8, and we were dipping into the L0, 1, 2, 3, 4, the lower or the later spectral types, which doesn't necessarily mean lower mass because you don't know the age, but colder temperatures. And so we had a very optimistic number of what we thought we were going to yield. And then we had some preliminary results of the survey where we give some numbers, but I don't have a good one for you. It's also, people have been, TRAPPIST was discovered very early on.
Yeah.
The TRAPPIST is named after the telescope that was used to discover it. It has another name.
Which is named after a Belgian beer as well, yeah.
Which is named after a Belgian beer, right. But it's almost like they got lucky-ish because they kept looking at others and there have not been another yield like what TRAPPIST yielded. So
it could be that these systems are just, they're out there, but they're just rare. There's not.
Yeah,
which is really interesting because it seems, certainly going to the moon angle, when we look at, simulations of how Jupiter's moons formed and Saturn's moons formed, as we understand them, we put this in proposals all the time, it seems like moon formation is an inevitable outcome of planet formation. Like, you just can't make that planet without forming a disk, which inevitably forms some remnant of moon systems around them. So it's pretty intriguing if brown dwarfs, for whatever reason, and these very low mass stars don't always do that. That implies something different happens in some fraction of the time.
Yeah, it's a question of does it become inefficient to do this in some conditions? Is it because of the natal environment they're a part of? Because brown dwarfs are the runt of the litter of a star formation process. And if it's a very dense star forming area, that means there's going to be a lot of big bullies around, possibly. This is also me spitballing because we don't know. We're not totally sure what could affect all of the bits that come out later that say, does it have a planet or does it not have a planet? But I'm not telling you there's none. I'm saying people have been looking, and I don't think we've done a very robust statistical check yet for me to say to you, oh yeah, they're definitely rare, like TRAPPIST was rare, and Pines is just not finding them. Because it's hard. It's very hard. We're in the beginning stages of trying to find rocky worlds around brown dwarfs.
That's what makes this exciting, I think, is that there is so much to do. And, talking about comparing to the solar system and this continuum of going from Jupiter to small stars, I want to talk about rotation. We know that sun-like stars gradually spin down over time. So presumably the sun, many years ago, billions of years ago when it was first born, would have been spinning much faster, and it gradually loses its angular momentum through basically accelerating particles along its magnetic field lines, and it could get flung far out, and eventually that ebbs the star of its angular momentum. When we look at Jupiter and Saturn, they still seem to have a lot of their angular momentum. They're still spinning pretty fast, like every 10 hours pretty much for the two planets. And so it seems like maybe they've lost some angular momentum, but it's definitely not as efficient as what happens with stars. For brown dwarfs, what is our expectation, and what have we found for their rotation?
Yeah, my group has done a lot on this. A postdoc that's worked on my team, Johanna Voss, is one of the leading experts on this. She's now a professor at Trinity College in Dublin. And what brown dwarfs do, which is similar to planets like Jupiter, is they spin fast. So they have a pretty rapid spin. And that is largely because they're born with an angular momentum, and they have a radius, but they contract. So it's like a figure skater pulling her arms in. And when you can think of figure skaters as they do it, do they spin faster or slower? They start spinning faster. So we see this rapid rotation amongst them that we thought might even help us do the opposite that stars do, where faster spins might mean that they're older. But that doesn't quite correlate like that. We haven't quite figured out the potential interaction with the magnetic field of these objects. There's probably some other extra mystery, because what we tried to do is take a sample of brown dwarfs at many different ages, field objects, and then a couple of different objects that are in known moving groups or nearby clusters.
Just to break this down, if it's in the field, that basically means it's old, it's mature, it's left its nursery. If it's in a cluster, it's still kind of in its nursery a little bit, and so you'd expect them to be younger. Just to break down that jargon a little bit. Right.
So the field, yes, when we say the field in any kind of part of astronomy, we're just referring to, we're not totally sure how old it is, but it's not in a cluster. Our sun is in the field. It's in the disk of the Milky Way. So we don't really know the age, but it's probably not less than 2.5, 3 billion years old. So when I say field, I kind of mean middle-aged like our sun. And then if you're in a cluster, you can still be old. You just have a better shot at having your age calibrated. So I should say either you're like our sun, kind of middle-aged, or you're very young. Less than 1 billion years old is what I would call very young. That's also debatable. Some people just want it to be 1 to 2 million years old to call it young, but I call anything really younger than a couple of our close-by clusters on the young side. So what we did was we tried to sample brown dwarfs in every single age-calibrated group we could find, and then looked at their rotations to see if there was a correlation, like, is there a spin down, is there a spin up?
And this is from the variability that you're using that rotating cloud as the cloud. I would guess this is how you're doing, because that's how we do it for stars.
What we did, it's the same way you do it with, we used the Spitzer Space Telescope. It was primary Spitzer Space Telescope in order to stare at the object and watch as it spins. They don't have sunspots,
right,
but they have holes.
They have features.
Yeah, they have holes in their clouds, basically. At least that's what we're assigning them to. And we measure their rotation rates that way.
Rather than doing it spectroscopically, we should look at line broadening. That's probably tricky for these objects.
We've done that as well, and we're able to get, when we do that, we have measured V sin I, the rotational velocity of these objects as well. That is way harder, because you do need a high resolution spectrum in order to get that.
Yeah.
for the most part, when I'm talking about rotation rate, which we do have for a very large sample of brown dwarfs at this point, large meaning, I don't know, 150, something like that, maybe 200. That for us, that's a lot.
Yeah.
And that sample, only a small portion of that, say 50 objects, maybe 60, has a high resolution spectrum. So you could also get the V sin I and the rotational broadening. But anyway, the point is that brown dwarfs rapidly rotate, just like Jupiter does. So
you found that in all these stars, that these brown dwarfs, they're just all rotating fast?
They rotate fast.
For any age?
Yeah. I mean, the problem is there's also a bias, because in order to measure the rotation rate for them, you also have to have a spot to measure. You have to have something to monitor.
Right.
And not all brown dwarfs have something. So some of them come up with no rotation.
So it can't be too uniform. If it's too uniform, there's nothing to grab onto.
Right.
Yeah.
So we're kind of limited to which objects we're actually allowed to measure this for, which probably biases our sample. But for the ones that we do measure, they rotate pretty fast. And we do see that the younger ones rotate slower than the older ones, meaning that you're witnessing that arms coming in of the figure skater with the contraction of the radius of the brown dwarf.
Oh, wow. So they actually do they actually spin up as they age a little bit.
That's right. Yeah.
Opposite of what we normally would think of for older stars. So how fast is fast? Like an hour rotation rate?
The fastest is on that order. And 1 to 2 hour rotation rates, something like that.
That's intriguing thinking about, again, the companions, because obviously the Earth used to be spinning much faster. It's thought to have had a rotation rate of around maybe as fast as 3 hours, maybe possibly 6 hours. And so that fast rotation rate was ebbed away because of tides with the moon.
Yeah.
And the moon was pushed out, right?
Yeah.
And if the Earth was spinning slower than the moon's revolution, if it happened that the Earth was born slow spinning, the moon would have come in and actually collided with the Earth. But the fact that the Earth is spinning fast is what pushes the moons out.
Yeah.
So I wonder if, especially, I mean, for the Galilean moon system, there's a whole bunch of them. They have resonances, but for an isolated moon, it might push their moons further away, and that would maybe explain why you're not seeing them in transit, right? Because then if they're far away from their brown dwarf, the geometric probability of getting it all lined up decreases.
Yeah.
Could be fun to think about.
I mean, there's a lot of levels to this too. You brought up 2MASS 1207, which people argue about what to call that system. Is it a binary brown dwarf system? Is it the first ever directly imaged exoplanet? Most people don't like calling it the first ever directly imaged exoplanet because it's orbiting, as you noted, like a 25 to 30 Jupiter mass brown dwarf. But that's kind of widely separated.
Yeah.
50 AU or something like that with that system. Mm-hmm. So unclear how it formed. Could it have been closer in and then pushed out, and then would that have impacted the 2MASS 1207 rotation rate? I don't know 2MASS 1207's rotation rate. I don't know that we've done it. But now that we've brought this up on this podcast, I'm going to go look it up when I leave here.
Interesting to check. Because it's meant to be slow then. It'd be slowed down.
It should be slower.
Yeah.
That one is a late type M. That's an M8. That's like a TRAPPIST.
Yeah.
It's TRAPPIST temperature, but not TRAPPIST mass. That is much lower mass than TRAPPIST.
So your team obviously does a lot on these atmospheres. We're talking about the clouds, which is already like interesting. We just swept through that very quickly, but these are kind of like small stars, and they have clouds, which is already amazing. And we know that conclusively now from many, many observations. What else are we discovering about the atmospheres of these brown dwarfs?
Oh man, these atmospheres are so complex and they're so annoying. Nothing is straightforward with them. So we are not sure about the equilibrium status of the atmospheres. So the objects are dominated by, they have clouds, and not all of them have the same levels of clouds.
What kind of clouds are we talking about?
Yeah.
Not water clouds, I assume.
Yeah, well, okay. So at the highest mass end, when we say clouds, it's too universal. It's different throughout the warm ones versus the cold ones. At the warmest ones, the warmest brown dwarfs, they're too hot for clouds. And then you step in to the the warm, low mass end of brown dwarfs, and you get sand clouds, silicate clouds. You get these clouds of corundum. We actually are not totally sure corundum's there. But if you put the right impurities in corundum, you get sapphire and ruby. They're gems. It's beautiful. And those might be held together in grains in the upper atmosphere of these objects. What we definitely know is that they're probably made up of, if you ever come to the American Museum of Natural History, there's a hall of gems and minerals, and we have entire cases of SiO2, quartz, and a variation on quartz. And I go down to that hall all the time just to stare at these walls of, these are things that we've pulled out of the earth here. These things are in the atmospheres of these objects that I study. It's awesome to see what they look like in different forms here on Earth. But they would be floating around in the atmospheres of these objects. That's on the warm end. But then, as they get colder, as you enter the T types, the clouds actually sink really low in the atmosphere and basically disappear, and methane just is the dominant thing. So methane gas just kind of sits on top and we can't quite see the clouds. So sometimes we refer to the T-types as cloudless. Then the sulfides show up, and sulfide clouds start coming in. And then by the time you get to...
Is that similar to what we have in... Does Venus have sulfuric clouds?
No, so that's too hot for... That is sulfur that's in the clouds of Venus, but this is slightly different variation that has sulfides in it. And salt clouds, so sodium chloride type clouds. You can get sodium, you can get chloride that can come together.
See, they're all things without analogy in the solar system.
Right.
Really theoretical, essentially.
Jupiter has all these clouds. They're just deeper in the atmosphere of Jupiter. They're not the part that people usually stare at, but they are there. Then by the time you get to the Y types, it's water ice clouds. So they have water clouds in them, most likely. We have yet to have the definitive paper on it. I did write a paper that was called Indications of Water Clouds, but it's an indication, but we still need a smoking gun feature.
So not only could you not boil on that world, you could also feel rain? Would they precipitate?
We don't precipitate. Would it precipitate? Maybe. Yeah, there could be rain out. You could get some rain out. That might happen. So there's somebody did write a paper, a guy named Jack Yates. He wrote a paper on whether or not you could have life in these water clouds. And Carl Sagan had done the same thing for Jupiter. Could you have little jellyfish type things that existed in the clouds of Jupiter? Where there's water, there's life usually. But it's kind of a tricky game because you'd kind of rise and then sink, and you'd have to exist only in this small area of the atmosphere. So it doesn't seem as likely. But it's still out there as a concept.
Yeah, that's fun.
Yeah.
So there's a huge amount about these atmospheres. I guess we could talk all day about atmospheres, but there is one object that's been in the news recently that we should talk about.
Yes.
And it's your object. So yes, I think you call this W1935, right?
Yeah.
But the name, the full name is horrible. It's CWISE PJ 1935-1546. We get a hard name in exoplanets for giving things bad names. You guys have some real issues with your naming of these objects. So why is this object so amazing? Give me your version of what is so exciting about this object.
Well, okay, so a couple things on this. It brings together a bunch of the things we've talked about. That object, which is named after a catalog, so it's CatWise. So the WISE catalog we were talking about, the Wide Field Infrared Survey Explorer, is a NASA catalog that Kevin Luhman used to discover 0855 and Lumen 16AB, these crazy cold nearby ones. And it's called CatWise because it was a new version of it. And then it's just the coordinates of the object.
Okay.
So for sanity's sake, we'll just refer to it as 1935 from now on.
I'm with that. Yeah.
Okay, so 1935 was co-discovered really, by this crazy search we were trying to find things closer than Proxima Centauri. We wanted the closest, coldest brown dwarf. And a citizen scientist named Dan Castleton worked with myself and the Backyard Worlds team, as well as our algorithmic team that was working on, we were using machine learning and just more basic scientific searches, not just the like blink method we were doing with Backyard Worlds, as part of what we called the CatWise team. Dan presented us with this candidate object, WISE 1935, and said, I don't know what this is. We followed it up with the Spitzer Space Telescope and figured out that it was within I think it's 11 parsecs, so like 40 light years away.
Mm-hmm.
About 40 light years away, which was very close, and we got excited. But all we could get was the photometry on it. We didn't get any spectra because there's no instrument on this planet, literally nothing on this planet, that can help us see what that object is doing.
Because it's too faint.
It's too faint. So we had to wait for the launch of the James Webb Space Telescope to see what might be going on with this object. And it was part of a program that got time in cycle 1 where we knew nothing.
So that's the first year of open field. Everyone can propose for data.
Right.
So I guess, the first was in 2000, like 2 years ago now?
2020 is when we put in, It launched in 2020.
Yeah.
And we all were putting in our proposals that year.
Okay.
And it was, cycle 1 means that all of the scientists, we threw all our ideas in, and no one knew what the telescope could deliver. We had no idea. We knew what the instruments were supposed to deliver, but no one quite knew. Mm-hmm. So it was part of the original, we're just going to go after it and see what happens. And this proposal that I led was called Explaining the Diversity of Cold Worlds. And we wanted to know what this one really looked like. We wanted total confirmation that it was a Y dwarf, that it was a very cold compact source near to the sun. It wasn't going to be closer than Proxima Centauri, we knew that, but we also suspected it might have some strange chemistry in its atmosphere. And then the spectrum came back, and we saw something that we could not explain easily in the data.
So you've got like 40 objects? How many are there?
No, we got 12 in this program.
There's 12, and then this
12.
one just stands out amongst those 12.
This one stuck out like a sore thumb because of one little thing that it had going on. It actually had a clone, another object that looked very similar to it, which was also lucky on our part because the whole thing is these things are very diverse. It's hard to get them to look like each other. But this one had an object that it looked very similar to. It was a very close temperature to it. So they had a lot of features that were the same, except for this one thing, which was these things are dominated by methane gas. Jupiter has tons of methane gas too. Mm-hmm. Methane gas is very dominant in gas giants. Hydrogen is everywhere, and carbon likes to attach to the hydrogen. So you can get methane pretty easily. That's one carbon, 4 hydrogens. And this thing, instead of seeing it absorbing, which is what you usually see, it's gas, it absorbs. It absorbs. Instead, we saw it glowing. We saw it emitting. This object was glowing with methane, which was not making sense to us at first because it's too cold to have that happen. So we had to dive into some uncharted territory to explore the solar system a little bit more, look at Jupiter, look at Saturn, look at the gas giants in our solar system. And we discovered that they also have methane in emission. And for them, it's driven by an interaction with the solar wind, which causes an aurora to happen on them. But we don't have a host star. This thing is all by itself. It's all alone, no host star involved at all. And then we discovered that this is a similar problem in that we had extra energy in our upper atmosphere that must be leading to the methane in emission.
So somehow in this methane, then the electrons are getting excited essentially in these molecules into higher energy levels, and then as it's relaxing, it's emitting, it's glowing. This is all in the infrared though, so you wouldn't see this if you were parked outside in a spaceship. Would you see this emission? Is there a visible counterpart to it?
Yeah, well, that's the question. Is there a visible counterpart to this? And that I don't have an answer to. I don't think that I have been asked this by the press, and I didn't have a good answer because we'd have to do some calculations to figure it out, which I haven't done yet.
Okay.
So I can't tell you for sure there wouldn't be some sort of optical counterpart to this.
But if you had an infrared goggles on, you would expect to see
you'd see a glow.
some glowing off the poles, presumably.
Right.
Like that's what happens with Jupiter and Saturn. Yeah.
Yeah. I mean, this is similar to Jupiter in the optical versus Jupiter in the infrared, and Jupiter doesn't look like it has much of a glow in the optical that's related to this.
Okay.
But if you turn to the infrared or you turn to the ultraviolet, Jupiter has this beautiful ring around its poles that is indicating that there are atoms getting excited and emitting. And they're getting excited because the solar wind is hitting it and exciting particles. But then there's a second component for Jupiter and Saturn, and that is their active moons. So Jupiter has Io, the most volcanic moon in the solar system, and it is generating a torus plasma that interacts with Jupiter and gives highlights to the aurora. It puts auroral footprints on Jupiter. And because we don't have a host star, we speculate that our methane emission, which we think is auroral in nature, might be caused by an interaction with an exomoon.
That's amazing. So there could be, let me just get straight in the ingredients here. You require an energy source, which is the solar wind in the case of Jupiter, and you require a source of plasma, which in the solar system is the case of Io and the other moons for Saturn.
You could have the aurora without Io on Jupiter because the sun is providing the ions as well.
Yeah.
So it can supply the energy.
But at much lower density, I would think.
Yeah. Lower density. So it's a different component of the aurora in the solar system, what it gets from Io versus what it gets from the solar wind.
But so that's just aurora in general, but to see your feature of methane emission, do you require both energy source plus plasma source, a significant plasma source to get that? Or is energy source alone plus because there's already methane in the atmosphere, is energy plus methane not enough to create that? Why do you need the plasma here?
No. All we need the thing to be rapidly rotating so that it spins up, and we need it to have a strong magnetic field. And that way it's creating an environment that would be conducive to a plasma something could give it. So we need something to throw a plasma on it that's going to get nicely ionized and interact in the upper atmosphere. Mm-hmm. So all we would really need is then an Io to make this happen. We don't need the solar wind. I just mean the solar wind is one of two components that can make it happen on Jupiter. But
in your case, just to clarify, you require some kind of energy.
Yeah.
Which I guess there's energy inside the planet. So that's and you require something to be spewing out plasma.
Yeah.
In the local area.
The energy would come from an interaction between that plasma, and so this is why the language gets a little bit confusing, because it's sometimes referred to as auroral heating. So the interaction between that plasma and the rapidly rotating brown dwarf with a strong magnetic field would be the energy that would dump energy in when the plasma interacts with that environment.
Okay.
So that's how we're going to get the extra energy in. Because the energy is a reflection of what the aurora is doing. And that is a reflection of the interaction of that moon with your system, which is a rapidly rotating brown dwarf with a big magnetic field.
So what do we know about I guess I'm curious about the environment this brown dwarf is in. Is there a way this plasma could be supplied some other way? Like, for instance, just from interstellar plasma or...
Yeah, that has been proposed. So there's somebody named Greg Hallinan. Also, Melody Cow, Sebastian Pineda. These are world experts on brown dwarf aurora. This is not the first candidate for an aurora. This is the coldest candidate anybody has ever seen. And we're really left with not a lot of options when you're as cold as we are.
So in their case, they didn't need to invoke an Io companion.
They have invoked it, but there can be some more explanations.
Easier to do it a different way.
Yeah, so there's a really popular one. It's a late type M. It's like TRAPPIST, or it's like 2 mass 1207. It's very young, but so it's a brown dwarf in the sense that it's It's below 75 Jupiter masses. It's young. And in that, it might have some natal plasma still around it because it's on the younger side that could then feed back in and help. I think of it as like sort of burping that might happen with some natal plasma that's left over from when the thing formed. So that might be out there as an explanation. There is an alternate explanation as well, which is it could be a gravity wave that comes from the interior and moves out like an earthquake.
Not a gravitational wave. This is a...
Right, no.
This is like an atmospheric effect. Yeah.
Planetary effect. We'll call it that because it starts from the core of the object and then it pulses out. And that's been proposed for our solar system. But in our case, if it's moving out, other things would probably get excited as it left. It wouldn't just hit the upper atmosphere. At least in all the modeling that we tried for that, it looked like more than just the methane would pop. And right now, all we really see is the methane, which is in the upper atmosphere of this object.
Yeah, it's so intriguing. So if this exomene's there supplying this, I guess we could argue about exomene, exoplanet, but there's a companion there supplying this.
If the companion's there.
Yeah. I guess what's intriguing is you said this brown dwarf is spinning fast. Is that confirmed? Or is that just, you're saying that because typically brown dwarfs are spinning fast?
Yeah, we don't have a rotation rate yet.
Okay.
We have asked for the Hubble Space Telescope, TAC, fingers crossed, we'll find out about this soon, to give us time to measure the rotation rate. Because we could also ask for it with JWST, but Hubble's actually better for this kind of observation.
So I know why I'm asking that question, but why are you interested in the rotation rate?
The rotation rate will be linked to the full picture. If it's very slowly rotating, like really slow, this is not adding up appropriately from the dynamics of the plasma interacting to create the aurora. And there's some modeling that's been done. Sebastian Pineda, I mentioned, has some nice modeling in order for us to go from, we're looking for all the ingredients, as you say. Rotation rate plays a role because you have to be able to create enough, it's like torque with the magnetic field to drag this plasma around in order to get that aurora to happen. So a non-rotating object is just going to sit there statically. And we're not going to get an interaction with, it doesn't matter what the moon is doing. I don't think it's going to do much.
So the methane emission is just something else at that point.
And then maybe it's something else. We still have to come up with a reason, but...
I was almost going to say the opposite because I would have thought, so you're hoping for a rapid rotation rate.
Yeah.
But I was kind of thinking the opposite just because, again, of this tidal issue, because Io is very, very close to Jupiter, and so Io is obviously the closest moon. It's only 6 Jupiter radii away, so I'm not sure how close you need Io to be to have this aurora effect. But yeah, my expectation generally would be that it would, if this thing's rotating once every hour, it would be like tidally pushed out fairly fast. Unless is this a young system? Well, I'm not sure yet.
We have no idea.
Yeah.
This is all the mystery we're waiting to solve if people give us more. Age is hard to figure out no matter what. We'd have to find its group of friends in order to get its age really well. There's not a lot of good indicators of ages for brown dwarfs just really on their own. So
we need more data.
So if somebody will just give us more telescope time to stare at this object, we could solve a lot of things.
You heard it here. If you're on the TAC.
If you're on the TAC. I don't know that your audience is all TAC members, but if it was.
There could be one or two. You never know. So what else can we do to confirm this possible companion? Is there other observations? We've got the rotation period. Presumably, seeing this effect happen repeatedly would be nice to know this is a continuous effect. Is there other types of observations like the transits we've mentioned before? Anything else you're thinking of that you might try to do here? Yeah,
well, there's a couple of things. There's more confirmation of it definitively being the thermal. A thermal emission, meaning that it's the aurora that we suspect. And we have a prediction based on how we modeled the feature. So we modeled the feature, but all we had was a tiny portion of a spectrum. We got JWST data, but only from 3 microns to 5 microns, which is just a very small portion of the full amount of data we could get. And that was just one instrument from JWST, and it was one of the gratings that we could use on that, because getting time on that telescope's hard. But
I've noticed, yeah.
Yeah, you noticed, right? But we made a prediction based on our model of just that area of what would happen if the TAC were to give us mid-infrared data. So we want now them to give us time to look at the 5 to 14 micron area, because what we see, if it is what we think it is, there's another emission that we're going to see. And there's evidence that it's going to happen, because we did get a photometric point rather than a spectrum, because we didn't think that the TAC, the original TAC, in that first cycle with JWST where no one knows anything, we didn't think they were going to give us that spectrum. So we just asked for a photometric point, and that photometric point is very bright. And that is what I think is indicating that that extra emission is out there in the mid-infrared. And if they give us the time, we'll be able to demonstrate that there's nitrogen and water and some continuum out there as well that looks like it's brighter. And that would be the result of this thermal emission. If it's not there, that's also fascinating, because maybe it is some non-thermal equilibrium something. Yeah. I don't know what, but maybe. But we have it's so rare, you know this, right? So rare to be able to present to a time allocation committee a prediction that will lead you down 2 different roads. Just give me the data and I can have an answer that's exciting in either direction. Yeah. So we're going to try in cycle 4, the 4th cycle of our attempts to get JWST time. This is the 4th time astronomers have been allowed to ask for time. And fingers crossed they'll give us time to stare at this object discovered by a regular person named Dan
awesome.
Castleton. That has led to this awesomeness.
It's so exciting, and I really hope they give you the time. This is such a fascinating topic, and what I'm really hoping is that this is a TRAPPIST-1. Maybe this is too hopeful, like a TRAPPIST-1 analogy, where there's not just one Io. Because where you've got Io, there's actually the whole host of moons beyond that. There's like these 4 Galilean moons, which are kind of comparable mass. They're all in a resonance. And so you only need that Io on the inside to supply the plasma. And there could be a whole chain of things out there. And for me, that would just like tie this nice knot in the bow of, okay, here's a continuum. We can go all the way from the stars to the brown dwarfs to the planets, and have this, at least one example of a continuum. So I'd love to see that, and wishing your proposal the best of luck.
I hope you're on the TAC.
Yeah, me too. I could be. Yeah, maybe I could be.
You could be.
I don't know if I guess I don't. I think it depends whether I propose. I think they usually pick people who aren't proposing, right?
No, they ask everybody.
Okay.
Yeah.
Okay. So.
I mean, the problem we all have is that these time allocation committees, you never know who's going to be on it, and everybody, through their best intentions, has their own biases into what they think is probably the best science. Now, some proposals get outed because they're just not written well, or because the science case is just not strong enough to like appeal to the community. But then at the top, like maybe the top 15% or so, it's a game of luck.
Yeah,
it's a game of what the TAC ate for lunch. Like all of that could affect whether you get time
also,
or not.
are you being judged after lunch or before lunch?
I know, right.
That happens with judges with juries. Apparently, if a jury has just had lunch or just before lunch and they're making their deliberations, it has a big impact on the statistical chance of
it happens to us. I've sat on committees, I'm sure you have too, where you sit in the room and everybody's hungry, and so all of a sudden you're meaner. And then the proposals are suffering not from their own fault.
We need lots of snacks at TACs.
Yeah, I think they want that to happen, but.
So to finish off, you're involved. You're doing all this wonderful brown dwarf work, but you're involved in so many projects in the city and other things as well. I just want to give you a chance to maybe mention something else that you're passionate about, that you're working on, and where people can learn more about your work.
Well, I'll say one. The Backyard Worlds project, which is the citizen science project, where we could find something closer than Proxima Cen, maybe, I'm always telling people, this is the way to also make science as equitable as possible. It's very hard for anybody to just get access to researchers, and Backyard Worlds is just the open door. Like, come, go to our website, have a look. You can reach out to the science team once you start engaging in the project.
So just Google Backyard Worlds.
Backyardworlds.org, or
Okay.
just go to backyardworlds.org.
Okay.
And then jump in. And then the other thing I would say is that I have co-founded this project called 2030 STEM, which is a accelerator program for diversity, equity, and inclusion in science. And that is, we run salons that bring together leaders in the STEM field to discuss topics that would help make STEM more equitable. And then we write up the results of those salons in white papers that we are using as evidence for policy change that would help us ensure that parity is reached across all of the kinds of researchers that we might have working within our field.
This is all of STEM, not just...
All of STEM. It's not just astronomy. I co-founded it with my best friend, who's a chemist. And so she brings the chemistry, I bring the astronomy. And then we invite every other STEM field to participate as well. But it's a little bit biased towards chemistry and astronomy right now. That's just because it's our fields. But we cover topics like mentoring, what's the best exercises for mentoring, or pathways to leadership, access to capital, all of the aspects of STEM leadership that needs attention if we're going to make sure that we have no biases against any one gender or race in science.
Great. That's wonderful, Jackie. Thank you so much for joining me today. So check out those. I'll put links down in the description for more on that information. But thank you so much for joining me today.
Thanks. This was fun.
Yeah. So that was my conversation with Dr. Jackie Faherty. I hope you enjoyed it as much as I did. I'll put some links down below in the show notes that link to her website and her research in case you want to learn more. Especially, I want to point out some links I'll put down to the BDNYC group, and especially if you are a student who is looking for research opportunities in the future. BDNYC recruits many students every year, from high school students and undergraduate students, and I've seen those students go on to do wonderful things, be very successful. They make great posters and talks and even papers. So if you are thinking of dipping your toe into research and you happen to be in the New York area, look, BDNYC is something you really want to check out. So please do look at that down below in the show notes. So brown dwarfs, what to say about brown dwarfs? So the thing I want to finish with about this is, of course, the moon connection. Of course, I'm going to talk about the moon connection. It does look, I think, increasingly likely that, there's already this object, as Jackie and I spoke about, that has hints, kind of indirect evidence, we might say, of exomoons already. And that in itself is not actually completely novel. There are other objects from microlensing and of course from transits which seem to hint at exomoons being out there, even from direct imaging, circumplanetary disks. So we are seeing many, many clues of exomoons being out there. Of course, we still want the slam dunk. We still want to see that completely unambiguous detection of ideally even a whole system of satellites. That's at least what's driving me forward, to get to that point where we just have the crisp, clear signal. We might get that with brown dwarfs before we get that with planets. And yes, we can argue about how to define that boundary between planets and brown dwarfs, but certainly if it's an isolated object that's just out there in the depths of space and it's around 10 Jupiter masses with a moon around it, or should that be a planet around it? I don't know. That's another whole discussion. That certainly establishes, if nothing else, forget about the definitions, that these brown dwarfs do form companions. Let's just say that. They do form companions around them. That's a huge step forward, a huge step. For me, it doesn't quite resolve the intellectual itch that I would still have. And that's not just, for the sake of doing research for the sake of doing research, but genuinely I still would have the intellectual question as to whether planets, the sorts of planets that we know of in the solar system, things like Jupiter, things even like the Earth, do those things often form moons? So discovering moon-giant brown dwarfs, I think it's going to happen. I think it may have, there's already hints of it being true with this most recent data. I still hope that it doesn't put us off continuing this journey, to keep going and trying to find moons around planets as well. But it just goes to show you how diverse nature is, that we may be getting companions, binaries, even trinary objects all across the universe, at all different scales. And the universe really doesn't care fundamentally what we call these things. It doesn't care whether we call them planets, brown dwarfs, stars, moons, worlds. Use whatever language you want. Pluto her feelings are not hurt that it got demoted to dwarf planet. All of these objects are fascinating and rich, and they are teaching us about the different scales and diversity of how these truly worlds are being manufactured and evolving in the universe. And all of that connects back to our own story. At least for me, that's the connection I see. Trying to understand our uniqueness. Where do we fit in to this picture? Where does the Earth fit in, the sun fit in, the solar system fit in to this giant picture of the vast array in which the universe can arrange things into different combinations and produce different things? So brown dwarfs are a very important part of this puzzle. I really do hope that we see some more fantastic results from JWST very soon, because it is one of those areas that JWST has enormous potential to be transformative. And hey, let's hope that the TACs are favorable to both, TACs being the time allocation committees, that they're favorable to both JWST looking at brown dwarfs and of course exomoons. Of course, we don't want to give up on exomoons as well. But a rich diversity of stuff. And of course, at the end of the day, this is all interconnected. We need all the pieces of the pie to really fit this puzzle together. So I'm inspired from this, speaking of Jackie, she's very energizing. I always get a huge amount of inspiration and energy just from feeding back off her through that conversation. I hope you did as well. And if you are enjoying these conversations on the Cool Words podcast, I'm going to say the way to support what we do here. You'll notice there was no ad on this podcast. The way to support what we do here is to go to coolworldslab.com/support. That's coolworldslab.com/support. There you can become a donor to my research team, the Cool Words Lab, where of course we're looking for exomoons and all sorts of wonderful other stuff out there in the cosmos. And when you do that, you are essentially supporting not only the podcast, but really primarily research. And the reason why that's so important for the podcast and also for the main YouTube channel is it kind of frees me up to make more of these things in the first place. The less time I have to do writing proposals and grant applications, because I'm being essentially helped and buoyed by your support, means the more of this kind of content I can create. So if you want to support us, it's the best way to do it. And you can have the comfort of knowing that your money is actually supporting real astrophysics research. So please do check it out, coolwordslab.com/support. So thanks as always for watching, and I'll see you in the next one.